Good morning. This is Miss Billerbeck, and we're going to talk about 5.3 step functions. So, a step function is a piecewise defined function that consists of constant pieces and it looks like steps. So, here's a step function right here. So, we have the range is y and the domain is x. So we see that x is part of this little step here for quite some time. So y is a constant value for all of these x's. And then the open hole means that it's not part of that y, that range for this x, but it's part of this part of the step for and that y value when we are at this value of x. So a step function, there's a few types of step functions. So the ceiling function is a kind of step function that rounds numbers up to the nearest integer. So a ceiling function, the open value will be at the left side and the x values will round up to the next integer. Okay, so see how the open values on the left side, we round up to the next integer for all of these values. Okay, so that's a ceiling function where we round up. So we would write the ceiling function as f of x equals this x, which looks like this. Let me write this a little bigger so you can see. So we're looking at f of x equals, and then this is a oddest little bracket. It's a bracket that's it's not complete, but it has a little bend at the top, meaning the ceiling. Okay, so the floor function is the opposite of the ceiling function. It's a kind of step function that rounds the numbers down to the nearest integer. So now the included point is at the left side and the non-included point's on the right side. So if it's any of these x values, it rounds to the lower value, the constant value of y. Okay, so instead of the little bend being at the top, the little bend's at the bottom. So this looks like f of x equals, and now we're going to bend it down at the bottom to show it's a floor function. Okay, so we're going to examine those today. All right, so first, what is the graph of the ceiling function for the following data? So first, let's figure out, well, what is the following data? So let's see if this pen will write. So if we're rounding, so it's a ceiling function, so we're rounding up. Now when we're dealing with negatives, that's a little harder. So maybe we should try starting with rounding up on the positives. So when we round up at 3.8, that's 4. That's the nearest integer. The nearest integer for 1.4 would be rounding up 2. This one would be 1. Now this one, rounding up to the nearest integer, it's negative now, but the next integer is 0. This next integer is negative 2. This next integer is negative 4. And the next integer here is negative 7. Okay, so that's rounding up to the next integer. So we really need to be comfortable with the number line to know that negative 7.3 is smaller than 7. Negative 7. Negative 4.7 is smaller than negative 4. So that's rounding up to the next integer. Okay, so if we were to graph that, this data, okay, so we have at x is negative 7.3, that's right around here. We have y is negative 7. So at negative 7.3, we're at y is negative 7. Now this is a ceiling function, so we know that it doesn't include 8, but it all the way to 7, it's included. Okay, then if we were to graph, move this up here, if we were to graph negative 4.7, negative 4, so down at negative 4.7 right in here, okay, so that's all these values, we're at negative 4. So we have a step function right here where it doesn't include negative 5, but all of them will go to 4. So we can kind of see that we could just, the ones that are, well, we'll plot these and then I'll show you the other steps. So this one, negative 2.9, so that's very close to here, but that's down, it rounds up to 2. So it means all the values of the domain here would go to here and include negative 2. Because negative 2 itself would just round to negative 2. Okay, at negative 0.5, right here, that would round to 0. So right here, we go to 0. Okay, and then at 0.3, which is right in here, we're going to go to 1. So we see, oh, we have this, we're going to 1. At 1.4, that's right about here, we're going to round to 2, which is here. So we have an open point here, we're rounding to 2. And then at 3.8 on the x right here, we're rounding to 4. So we would have an open point here. Now from this, we can see which steps we didn't have on our data here to show the ceiling function. So we could write in this one, and we can see that it makes a beautiful step pattern, just like a stair step. For all these, okay, and it just keeps going. So that would be the ceiling function for what we were looking at. Okay. All right, so let's look at, well, if that's the ceiling function, let's look at, well, what is the floor function? All right, so for this one, we're going to, for floor functions, we round down. So if we have negative 7.3, we'd round down to negative 8 because that's a little smaller than negative 7.3. This one, we're going to round down to negative 5. This one would be negative 3. It's a little smaller than a negative 2.9. This one would be negative 1. This one, rounding it down, would be 0. This one would be 1, and this one would be 3. So when we round it down to the nearest integer, then this is what it would look like. So we can see, oh, hey, they're just one different. Okay, that's kind of interesting, the pattern between those data. If it's a ceiling function, it's just one more than the floor function. All right, so I'll graph that using this. I don't think let's see, yeah, we'll use this one. And let me use a different pin for that. Okay, so if I start with this data, I have at negative 7.3, which is right around here, I go down to 8. Okay, so at 8 is, if it's negative 8, it's already negative 8. So I'm going to have an open point here at negative 7. All right, if I'm at 4.7 right here, I'm going to round that to -5. So if it was -4, it would have stayed at 4, so I'm going to leave an open point there. Okay, at -2.9, I'm going to round that to 3. And I'm going to have the open point at -2. And then at -0.5 right here, I'm rounding that to -1. So -0.5 is -1. So that includes -1, but it doesn't include 0. And then the 0.3 does include 0, but it does not include 1. And then the 1.4 does include 1, but it does not include 2. So remember, the range is always constant, so that's why we're making these lines. And then at 3.8, we round that to 3, so that's back here. And then all the x's in between are right there. Okay, so that's our floor function. And let's fill in the missing values that weren't in our data. So this would be right to here. Okay, so it makes this beautiful stair pattern where you could just walk up these stairs. Like those fancy modern stairs where if you accidentally step too far, you step through the stairs. Okay, don't want to do that. That's pretty scary. All right, so let's compare the two side by side. So we have the ceiling function. The open point is on the left, the closed point's on the right, and the floor function, the closed point's on the left, the open point's on the right. Okay, and let's write how we would designate that. So the floor function would be f of x equals, and the bar is going to go down like that. And this ceiling function, we would write f of x equals, and the little bend is at the top, like at the ceiling. Okay? So in math, we try to make the symbols pretty relevant. So if it's super hard, maybe it's not correct, okay, as far as the symbols. So let's take a look at some real life problems. Okay, we will always send packages one way or the other. So we'll be paying postage, whether it's UPS, FedEx, or the US Postal Service. So the postage for a first class letter weighing 1 ounce or less is 47 cents. Okay, so each additional ounce is 21 cents. So the maximum weight of a first class letter is 3.5 ounces. So that's good to know your boundaries. So we want to write a function to represent this. So we're going to write f of x, and we'll start with the first of these, that the first, if it's 1 ounce or less. So that tells me my restriction on the domain is going to be 0 is less than, x is less than or equal to 1 ounce. Okay, so I don't have 0 ounces included because if I'm not sending anything, I'm not paying anything. Okay, so if we're going to represent this as a function, we'd write, well, for that restriction on the domain for this piecewise defined function, I am going to write this as a ceiling function, right, like that, because anything that is in between this is going to be 47 cents. So it's just going to round up, and it doesn't include the lower end. So it's a ceiling function. Okay, so then once we're over 1 ounce, then we have to pay, each additional ounce is 21 cents. Okay, so this is where it gets a little bit interesting as far as how to write this one. So we know that we're going to be paying 21 cents for each additional ounce. Okay, and we're going to have a range for that. So our range is going to be, or the domain is going to be between 1 for the x, and then it says that the letter can't be more than 3.5 ounces. So it can be less than or equal to 3.5 ounces. So this would be this, but we still have to add a little something, because what happens if it was x? If we had this in here, we would still have to have 0.26, because we see 0.26 plus 0.21 equals 0.47. So that encompasses all the areas of the first ounce. Okay, so if x is 1, okay, then this would follow that same line. So we're starting at a y-intercept of this when we're using this. That's all it's saying. We might want to graph that just so we understand that a little bit better. Let's. Okay. All right, so let's assume that this is 20 like this. Actually, well, we'll do our best with this graph, okay? So we're just going to do the decimal version of these. All right, so for the first ounce, which is, oops, these are ounces, so we don't have decimals. The range is what has the decimals. Silly me. Okay, so there we go. Take those decimals off. All right, so for 1 ounce, we're up at 47 cents. So from 0 to 1 ounce, we're right here. Okay, as soon as we have an additional ounce after that, we are going to be paying 21 cents in addition to the 47. So if we look at the 0.21 times 2, because we're rounding up, and then plus 0.21, we know that we should be paying 0.47 plus 0.21 for the next ounce. So we have 0.68. So if we use this, this gives us 0.42 plus 0.26. So let's add that together. That gives us 0.68. So that's why we've set it up like this, where we're adding the 0.26. Because we're not going to start with 1, we're starting with 2. Okay? So we just needed to make sure that 0.21 plus 0.26 is that 0.47 when we add it together. But now we're going to do the second ounce, where we're adding that 21 cents. Okay? So let's go ahead and look at this. So after the 21 cents, we have at 2. So we're just going to, we have 0.68. So that's about right here. Okay, so it's just going to be a step function like that, where the difference between these will be 0.21. This is rising up 0.21 in between. So the next one at 3 ounces, we would be up at adding 2 to the 6/8, so that gives us 8.9. So we're getting very close to that. So it would just look like that with the postal rates. Okay, so that's why we came up with this as our additional part of the function. So remember, if x is 1, that should add up to that. But once x is 2, it represents the additional 0.21 for each additional ounce. Okay? All right, let's try another one. So we have renting a karaoke machine costs $30 for the first hour, any fraction of that hour. If it costs $10 each hour, or any fraction of that additional hour after the first hour, write the function to represent this. Okay, so we're going to start with the first hour. So we have f of x equals, and we are going to write, so we have $30 for the first hour, or any fraction of that hour. So that means for this restriction of 0 is less than, x is less than or equal to 1, we are going to pay $30, and we're going to put a ceiling function on that. All right, then on the next part, it says it costs $10 each hour, or any fraction of that additional hour after the first hour. So write a function to represent this. Okay, so 30 minus 10 is 20. So we know each hour is going to change by 10. So we're going to keep that as a slope for the ceiling function. But we're going to have to add a y-intercept of 20, because if this is 1, 10 plus 20 equals that 30. Okay? But we have the restriction that x is going to be greater than 1. So that's how we would write that function, that ceiling function. So will you save money if you return the karaoke machine in 15 minutes earlier than at the end of the hour? Will you save money? No. You will pay the same amount of money that you're going to pay for that full hour. So you might as well keep the karaoke machine until the end of the hour, and then turn it in really fast so you don't have to pay for the next hour. Okay, well, that's it for this section. I hope you have a wonderful day. Bye-bye.